In some previous video topics, we had established that the EM wave is the propagation of the electric field, which I'm showing here in red, and the B field, the magnetic field, at right angles to one another as energy is transported through space. The wave is going to move through a medium as what we call a traveling wave, and it will propagate as it goes with a finite velocity that we call the propagation velocity, mu sub p, or the phase velocity. And we were able to relate the propagation velocity of the traveling wave to two other parameters of the wave, the angular frequency and the wave number. And so we wrote that the propagation velocity of an electromagnetic wave traveling in any medium can be found by taking the angular frequency and dividing it by the wave number. An angular frequency is measured in radians per second, and wave number is measured in radians per meter. So you can see that radians per second divided by radians per meter just gives us units of meters per second. And we can also modify the equation that we have here using our known relationships between angular frequency and between wave number and wavelength to write a couple other equations for propagation velocity. So that first relationship that I was speaking of is angular frequency omega is equal to 2 pi divided by the period of the wave, and the second relationship is that wave number is equal to 2 pi divided by the wavelength of the wave. Oftentimes we'll rewrite this top equation as equal to 2 pi times f, the cyclic frequency, more commonly called the frequency. And so if we take these two equations and we sub them into here, what we result in is that the propagation velocity of an electromagnetic wave is equal to 2 pi f divided by 2 pi over lambda. And we work that out. The 2 pi's cancel. Lambda comes to the numerator. And we find out that propagation velocity is just equal to wavelength times frequency. Although this equation here and this equation here are mathematically correct relationships, they're technically correct. I kind of think that these equations are looking at the situation backwards. And the reason I say this is that they imply that propagation velocity is dependent on angular frequency and wave number, or they imply that propagation velocity is dependent on wavelength and frequency, and that's really kind of backwards. In fact, it's the opposite that's true. The properties of the traveling wave, wavelength and wave number, lambda and beta, those are actually dependent upon propagation velocity, not the other way around. So I really think that it's better to write that, to rearrange these, and instead of saying mu p equals omega over beta, I really think it's better to write beta is equal to omega divided by propagation velocity, and I think it's better to write that wavelength is equal to propagation velocity divided by frequency. And this really shows us the relationship. It more clearly indicates that the spatial terms, beta and lambda, are dependent upon propagation velocity in both of these cases. Okay, so now we know that to calculate either wave number or wavelength, we have to know both frequency information and velocity information. But where does this information come from? Well, we'll start that by stating that, well, frequency is pretty easy to come by. The frequency of an electromagnetic wave is set by the source of whatever the radiation is. So, for example, you would set the frequency of oscillation in your function generator in a lab experiment. So you've got your voltage source, and you set the peak value, and then you also set the frequency. So if you were to measure this, for example, you would have V of t is equal to whatever that peak value is, cosine of omega t, which we know that just by substitution of variables, we get Vp cosine 2 pi f t, right? And this is the value you set on the function generator in your lab with your amplitude. And this is the value here that you set with the frequency knob. So you might set this from anywhere from 0 to 10 volts. You might set this one from 1K, 10K, a megahertz, something like that. And this is exactly what other radiative sources do. Cell phones, radio stations, etc. Whenever they create an electromagnetic wave, they're setting the frequency of the hardware. So that tells us where wavelength and frequency come from. But what about propagation velocity? How do we know how fast an EM wave is actually going to travel in a conductor or in free space? And it turns out that this is dependent on two properties of materials that we mentioned previously, the magnetic permeability and electric permittivity. So I'll just remind you what those look like. That's electric permittivity, epsilon, and mu is the magnetic permeability. And electric permittivity is measured in farads per meter, and magnetic permeability is measured in henries per meter. And the speed at which an electromagnetic wave is going to propagate through a material is then calculated using these two quantities, and it's given by this formula. Propagation velocity is equal to the square root of the electric permittivity times the magnetic permeability, all taken to an inverse there. So this is actually the relationship by which we know how fast any EM wave travels through a material. So magnetic permeability and electric permittivity, they're properties of all materials, and for a vacuum they are mu0 equals 4 pi times 10 to the minus 7th henries per meter, and for a vacuum we call it epsilon naught for vacuum permittivity, and that's equal to 8.854 times 10 to the minus 12 farads per meter. And these, again, that's vacuum permeability, that's vacuum permittivity. If you were to plug 4 pi times 10 to the minus 7th and 8.854 times 10 to the minus 12th into this equation here, you would get the speed of light 3 times 10 to the 8th meters per second, which is just the propagation velocity of electromagnetic wave in a vacuum. As we can see from the units of Henry per meter, magnetic permeability is basically a measurement of the ability of a material to support the formation of a magnetic field. And said another way, it's the degree of magnetization a material will obtain if we were to apply a magnetic field to it. Materials with high magnetic permeability, like a metal or something similar, we say they're easily magnetized, meaning that they can easily support the B field. Looking at electric permittivity, the units of farads per meter tell us that electric permittivity is a measurement of the ability of a material to support the formation of an electric field. Said another way, it's a measurement, this number is a measurement of how an electric field will affect the material that supports it. Materials with high electric permittivities tend to resist E fields, meaning that insulating materials like rubber and polyethylenes tend to have high electric permittivities. If we wanted to calculate the electric permittivity and magnetic permeability for materials other than the vacuum condition or free space, we have to use relative permittivity and relative permeability. So if we're not in a vacuum, we say that mu, the permeability, magnetic permeability of a material, it's equal to the relative permeability of that material times the vacuum permeability. And almost exactly the same equation is used for permittivity. Permittivity of a material is equal to relative permittivity, epsilon sub r, times epsilon sub naught, the vacuum permittivity. What this shows us is that relative permittivities and relative permeabilities, they're just scalar multiples of the vacuum permittivity and the vacuum permeability. I've included on Blackboard a table of relative permeabilities and relative electric permittivities for you, for different materials, for different insulators. It's just copied from the textbook, so if you've got a textbook, that's a good reference as well. And you can find similar tables online as well. So now we've demonstrated that an electromagnetic wave will be delayed through a conductor as it travels due to the material properties, magnetic permeability and electric permittivity. This delay is one of the two primary reasons we need to use electromagnetic analysis in our ECET courses, but it's not the only reason. It's only half the story. The second major characteristic about electromagnetic waves that we have to consider is what happens when they change mediums. So what happens when they move from one material, or what we will call a waveguide, into another material or waveguide. And by waveguide, I just mean something that's carrying the EM wave. Most common waveguides would be just a basic piece of wire, but a resistor is also a waveguide, a capacitor is a waveguide, glass could be considered a waveguide, pipe can be considered a waveguide in certain situations. All these things can be considered waveguides. So all waveguides are going to experience what we call partial transmittance and partial reflectance when the medium through which the wave is traveling suddenly changes. So I've got a little video here. It's in the middle of the video. So you see this incident wave. It hits this line, which represents the change of material. This could be from free space to glass. This could be from one wire into another wire, something like that. But what happens is you've got this amplitude. Some of the wave energy is transmitted through. It's reduced, but it's transmitted through. And then some of the wave energy is reflected back. Neither of those peaks are as big as the incident wave. Neither the transmitted portion or the reflected portion is as big as the incident wave. And so you see that just some of the energy makes it through, while some of the energy gets sent back to the sending source. In electric circuits, a reflection like this occurs whenever there's a change in impedance in a circuit, either between two wires or when you're going from a wire to a load, and can have significant consequences in electric circuit analysis. Often what's happening is we're not just sending one wave, we're sending multiple waves, and so we get lots of these, what we call reflected waves, being sent back towards the source and are traveling back away from the impedance boundary. And what will end up happening is we get constructive and destructive interference of the incident wave here and the reflected wave here. And so we end up getting all these waves adding together, and we get this constructive and destructive interference of the wave patterns on a transmission line. So these two factors, the reflections that occur at an impedance boundary and the delay associated with an EM wave traveling through a material, those are the two factors that are typically ignored in all of your other classes, in undergraduate courses in ECET, and are the primary focus of what we're going to be studying in the rest of this course.